It is recording, and I do have audio. Okay. Hopefully no technical difficulties today. There you go. Y'all pass it around. Start with, do either of you have questions about the homework or last week? No? All right. It was pretty much conceptual stuff last week. This week, we're going to start actually tabulating and analyzing some of this data. Did either or both of you do your reading assignment? Have y'all read the chapter yet? Okay. Yeah, well, we'll probably won't do more than the first two sections today because we got 3 days to cover all of them. But first thing we're going to look at is getting the data collected, tabulating the data. If all you have is a set of data, then what you have is called raw data. You haven't processed it, you haven't analyzed it, you haven't looked at it, it's just raw data. A set of numbers, a sampling. Now, I do want to point this out. A population does not have to be people. Okay? It can be animals, it can be inanimate objects, it can be, it can be whatever. But the whole body of everyone or everything in the group is the population. Okay? Normally, when we talk about populations, we talk about people. But it doesn't have to be. It could be the population, could be all of the tables on campus. Okay? In which case, the tables in this room would be a sample. What kind of sample? It would be raw data, but it would be a clustered sample. Because we just picked this one little room and said, okay, well, here's a sampling of tables from the campus. Anyway. But I digress. Here in section 2.1, we're on page 42. They look at here. They've got, what is this? 10 rows of 5 columns. That's 50 of the wealthiest people in the world. Now, in this case, he went to how old they are. So the numbers are the ages of the 50 wealthiest people in the world, according to Forbes magazine. This would be the raw data. Now, we're going to, you know what, we'll get to the other kind of, we talk about raw data, but generally when you use an adjective to describe something, it usually is in order to make it distinct from something else. So we say, well, this is raw data, as opposed to what kind of data? Well, we'll get there later. Right now, let's talk about how we organize this raw data. We tabulate it, we put it in a table. And then we talk about the frequency distribution. Now, We're also going to talk about classes. Now, both of these words, frequency and class, they probably already have meaning to you. That meaning may or may not be what is meant by these words when we talk about statistics or analyzing data statistically. So let's talk about first, what does this mean? What is a frequency? Well, I'm a physicist and an engineer. So to me, I hear frequency, I'm thinking of something in terms of hertz, cycles per second, radians per second. It's not what statisticians mean. When I talk about a class, my background includes a lot of computer programming. And, well, welcome. Say again? Hola. Yeah, there you go. Just make sure you sign in. So if you've got any kind of programming background, then a class would be a subdivision of object-oriented programming. In this case, when we say a class, we mean a group or a grouping or a category that the raw data can be put into. Okay? The word I like to use is called binning. I doubt that you're going to run into it in the book, but I call it binning because if you're taking a bunch of anything, you have a range, you're breaking up a variable, you have a range of values that variable can take. Well, you divide that range into sections. And then you look and see where so that these are, this is the whole range, it's divided into sections. Now you take each instance of the variable and you find out in which one of these sections would it fall, would it land? And you start putting them in, whatever bin they go in. Okay? Then you count up how many landed in this bin. How many landed in this bin? Here, this one got 0, that one got 0, these two got 1 each. Those numbers, those tallies, those are the frequencies of the data. In other words, it's saying how frequently does one datum from this set of raw data, how frequently does it land in this bin, or in this class? Okay? That's what statisticians mean when they talk about frequency and classes. And these stupid erasers are going to start this nonsense again. They always migrate down to that end of the board. I don't know why or how, they just do. And it couldn't possibly have anything to do with me dragging them down there and leaving them. Okay. I think a good way to get this straight in our minds is to actually work through an example. You look on page 43, you will see where on the top of page 43, you'll see the frequency distribution for the raw data that's tabulated on page 42. These are the ages of the 50 richest people in the world, according to Forbes magazine. And it looks like there's only one on the list, one who made the top 50 list that was from between 27 and 35 years old. 3 that were between 36 and 44. 9 of them fell between 45 and 53. 15 of them fell between 54 and 62. 10 between 63 and 71. 3 were between 72 and 80. 7 were between 81 and 89. And 2 were between 90 and 98. So, in this case, the frequency distribution was, the tabulated data was divided into 1, 2, 3, 4, 5, 6, 7, 8 classes. Okay? The frequency of each class was in order 1, 3, 9, 15, 10, 3, 7, and 2. How frequently is one of the 50 richest men in the world going to be in his early 50s? Well, if we go, well, say 54 to 62, 15 times. That's the most frequent response. Okay. Let's work through example 2.1. We're going to look at some blood types. Now, what's the population of this one? It's a sample of 25 randomly chosen inductees in the United States Army, or in the military, Army inductees. Okay, we've got 25 of them. And let's look at the data. It's tabulated. It's ABB, ABO. Followed by OO, BABB. BBOANO. AOOO, AB, and finally ABAOBA. Now that is our raw tabulated data. So the next thing we have to do is set up a frequency distribution table. First of all, we need classes. Then we need tallies. Frequencies. And we'll round it out with percentages. Well, what kind of data is this? Right off the bat, we see it is not quantitative. It's qualitative. It's certainly nominal. It's categorical. Okay? We could assign an order in terms of alphabetical order, but that really doesn't apply. That's not what the letters mean. So, but because these are what kind of data? These are not continuous. These are discrete data. So we've got 4 classes: A, A, B, B, and O. And I bet I put it in the wrong order. Yep. Here, I'll reorder mine so they match, so it matches the book. A, B, O, A, B. Okay, A, B, O, and A, B. Those are the four classes. The next step we have to go through is tallying the data into the tally column here. So how do we do that? Start top left and go row and column wise. Starting at the top left and working across, we have A, B, B, A, B, O. Next row, O, O, B, A, B, B. Next row, B, B, O, A, O. Next row, A, O, 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 A, B. And finally, A, B, A, O, B, and A. That's our tally. Now we should have 25, right? 5, 10, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25. All right. Now we got to do, fill out our frequency column is count them up. We've got 5 in A, 5, 6, 7 in B, 9 in O, and 4 in AB. That is our frequency distribution. And we've already counted the tally. If we add all of these up, 5 and 4 is 9, plus 9 is 18, 19, 20, 25. So, now how do we write these as percentages? Frequency divided by the total, and then they're going to say times 100. There's I'm going to tell y'all just up front right now. In my mind, when I divide the frequency by the total, and I get that number between 0 and 1, in my thinking, that's a percentage. It's the ratio of the percentage. Okay? They, in the book, are going to call that the relative data. Remember earlier I said we have raw data? Raw as opposed to what? Raw as opposed to relative data. Here, they would say 5 divided by 25 is what? 0.2? Okay, I'm going to, another thing, make a mental note of this. Never, ever, ever under any condition, for any reason whatsoever, ever trust me to do arithmetic in my head. It just will not end well for any of us. Okay? Have your calculators ready when we do the arithmetic. I will need y'all. And right now is a perfect example. What's 7 divided by 25? Say again. 9 divided by 25? 0.36. Okay, one of you lied to me. Oh, this should be 0.28. Okay. So This is 0.36, and 4 divided by 25 is 0.16. Okay? Now, we multiply these by 100. So we agree with the book, and this becomes 20%, 28%, 36%, and 16%. Now I can move the decimal place too and do that in my head fairly accurately. What's this total up to? 100%. This column would total, if you add all of these together, somebody do it and confirm that it works out to 1.0 or 1.00. Got it? Okay. That is the whole exercise. You tabulate the data. You make your frequency table. You tally the data, the raw data, into the frequency table. Add up your tallies for your frequencies, and then if you need to, you find the percentages. Either the relative distribution, the relative frequencies, or the percentage frequencies. That's all you do. Every time, over and over and over and over and over again. But, as we're about to discover, it doesn't always involve categorical data like this. Sometimes it involves quantitative data. This would be, well, the next thing we're going to look at is called a grouped frequency distribution. On page 44, down at the bottom, you'll notice they added another column called class boundaries. Now, in this case, they've divided the group, they've divided the raw data into 1, 2, 3, 4, 5, 6, 7 classes. Now, we know from the classes that the range of the raw data here is every piece of data in the sample was greater than 58 and was less than 106. Or greater than or equal to, or less than or equal to. Okay, so and given the fact that these are all integer numbers, you might conclude that, well, these are discrete variables, right? Maybe they are. But if they were, they wouldn't have had a need for the class boundaries. Let's go ahead and recreate this table here. And we'll look at the class boundaries. We've got 58 to 64 is the first class. These are the class limits. '65 to 71, 72 to 78, 79 to 85. 86 to 92. 93 to 99. And then finally 100 to 106. Those are the classes. But we do not know that these are necessarily discrete data. These may not necessarily be whole counting numbers. It may be that these were measured values that have been rounded to the nearest. They've already been rounded to the nearest integer. Okay? That means, remember when we set up that bin? Instead of a continuous, instead of this, divided into 4 bins, here we've got and so on. Well, what if one of those data were actually 64.3? Where would it have landed in this binning, in this class distribution, frequency distribution? It would have landed somewhere in this gap between the two. Now, that's why we include class boundaries. When you make up your classes, there can be no overlap. Okay? We cannot say this class would be 58 to 64, this class would then be 64 to 71. That won't work. Because if one of those data is 64, which class do we put it in? It could go in either one if we make the class limits equal. So there can be no overlap when you set up your classes. And if you're setting, that means as long as you're dealing with a finite number of digits, okay, then there's always going to be a gap between them, between any two. We define the class boundaries for one and only one purpose. It makes explicit the fact that nothing did get lost in the gap between the classes. Okay? Now, that means you go one additional decimal place. In this case, we started off with integers. So you add one decimal place to that and go up and down by 5. 58 minus 0.5 would be a class boundary of 57.5, and 64 plus 0.5 gives you 64.5. Now, what's the next class boundary? 65. What would the boundary be? 64.5. And the other class boundary, 71.5. Here, 72 minus 0.5 would be 71.5 to 78.5. 78.5 to 85.5. And so on. Look at what's happening. These boundaries are exhibiting overlap. The very overlap we said could not happen with the classes. It's important for you to understand that by the time you've got the tabulated data, by the time you've got the raw data and it's been tabulated, you've got it in rows and columns or whatever, you're ready to start assigning it. You're ready to start binning it into this frequency distribution. It's already been rounded. Okay? And it's been rounded to one less decimal place than would be here. Okay? So if it fell right on 57.5, it would already have been rounded to 58. See what I'm saying? So in terms of your analysis, when you start actually counting and doing, binning the data and doing the tallying and all of that, you're never going to use these numbers again. Okay? These class boundaries, you're not going to use them again. So if something did land on exactly 71.5, it would have already been rounded. So this is never going to be an issue. What this does is this makes explicit, it formally makes it explicit that even though these data represent continuous values, they have already been dealt with, and they've already been rounded, and nothing has fallen between the gaps, in the gaps between the classes. Okay? That's the whole point and purpose of establishing these class boundaries. It formally makes it explicit that all of the data has been accounted for in the entire range, and there's no gaps. Now, in this case, we were talking about integer values. What if the data had been rounded before you got it? It had already been rounded to 2 decimal places. So this went from, we'll say, 53.62 to 62.84. Just making up numbers. What then would be the boundaries, the class boundaries? Because we know the next one here would be, this one would be 62.85. Okay? Because it always, the next class will always be an increment of 1 in the last digit of the data. Okay? So what will the boundaries be in this case? What's the boundary here? What's the lower boundary for this class? 53.62 minus one more decimal place of 5. So it'd be minus 0.005. That would bring it to 53.615. And the upper boundary would be 62.845. What would the lower boundary here be? 62.85 minus 0.005, 5 in the third decimal place, would become 62.845. The same, it will have the same lower boundary as the upper boundary of the class before it. I think it's fairly obvious that this is a little bit more complicated to work through than these integer numbers. Okay. That's why it was the first one we did with integers. But it doesn't have to be integers. It can be any number of decimal places, any number of digits. We got some rules. Those are the class boundaries. And then finally, we're going to talk about the class width. Okay, and this is one of the things you're going to be asked to do is to calculate the class widths in a frequency distribution. What's the width of this class here, 58 to 64? We'll just count it. 58, 59, 60, 61, 62, 63, 64. 7. What's 65 to 71? 65, 6, 7, 8, 9, 70, 71. 7 again. What's this one? 72 to 78. 2, 3, 4, 5, 6, 7. No, still be 7. Same thing here. 79, 80, 81, 82, 83, 84, 85. 7. 86, 87, 88, 89, 90, 91, 92. 7. 93 to 99. 7. 100 to 106. 7. The class width in every case was 7. Now, there are 2 ways you can find the class width. You can either subtract the upper boundary, the lower boundary from the upper boundary. Someone with a calculator, do that here. 64.5 minus 57.5. Gives you 7. What happens if you subtract the upper limit from the lower limit? Or, I'm sorry, what I said, but the other way around. Now, 64 minus 58. No, would be 6. It would not be the correct answer. If you're going to work with the class limits, then to find the class width, you subtract this lower limit. You subtract this lower limit from this lower limit. So you would subtract 65 minus 58. Or you could subtract 71 minus 64. But you subtract adjacent boundaries, not boundaries, the adjacent limits, not the 2 limits of the same class. So, let's talk about the rules for when you're doing an analysis. First thing you have to decide is how many classes to use and what will the width of each class be. So rule number 1, and I'm on page 45 if you're following along. There should be between 5 and 20 classes. Although there is no hard and fast rule for the number of classes contained in a frequency distribution, it is of the utmost importance to have enough classes to present a clear description of the collected data. So you want enough classes that you produce an accurate representation of the data. That you can actually see the distribution as it shapes up. If you find, and I'm just telling you this now out of the book, but if you decide, you've got a tabulated set of data, and you decide I'm going to divide this data up into, I want to make this a really high resolution graph, you start finding that you've got zeros. You've got zeros showing up in your distribution. Then that tells you that you've divided your raw data into too many classes. You don't need that many classes to give a good picture of that data set. Okay. The other side of that coin is if you just divide it into one class, and say, well, it's from 58 to 106, then that's not a distribution, that's just a tally, that's a summation. You're just counting the number of samples you took. So, the rule of thumb they give you in the book is 5 to 20. That's probably going to be a good numbers to use in the problems and examples they work in the book. In practice, that may not always be the case. The more classes you subdivide a frequency distribution into, the more resolute your description will be. But at some point, when you start seeing zeros show up in your classes, in your tallies, then you've resolved it further than the data supports. So back off a few classes and try to make sure you've got some data in every class, some tally in every class. Okay, number 2, it is preferable, but not absolutely necessary, that the class width be an odd number. Okay. What they're saying is, what would it be if it was an even number? What would happen if this was a 6? If these classes were subdivided into 6 instead of 7? Well, it would be 1, 2, 3, 4, 5, 6, 7. There would be one more class. Okay. But the only thing that would happen is the middle of the class would be something 0.5 instead of an integer number. Okay? They're saying that if you make the class width an odd number instead of an even number, then you will always have the middle of the class will be an actual data value. Okay? Now, I'm telling you, that's a whole lot of little Sheldon Cooper demons swirling around in somebody's head. There is. It doesn't make a lick of difference. You've got calculators to do the arithmetic. You've got spreadsheets and computers. Okay. The book says it's preferable. Well, it's preferable the way it's preferable that Sheldon Cooper knocks 3 times and repeats the knock 3 times. Okay. That's all I have to say on that. There's absolutely nothing wrong with even numbered class widths. But if anyone in the book asks you, well, then it's preferable. Rule number 3. Rule number 3 is not just preferable. It's not just a suggestion. It is imperative. Classes must be mutually exclusive. That's why we have these little gaps in the classes. That's why we set up the class boundaries to make explicit that yes, we know the gaps are there, we've accounted for this. None of the data is falling between the gaps. But you cannot have a class, so you cannot divide the classes up so that it cannot be possible for any one data to be able to be put in more than one class. Okay. Just no overlap between the classes. 4, the classes must be continuous. Even if some of the classes have 0 in the tally, so there's no data in some of the classes, they still need to be continuous. I know this is kind of contradicting what I just told you a minute ago, that if you start getting zeros in the classes, well, then you're dividing up the class, you're dividing things up too finely. Sometimes you may not have a choice. If you're dealing with 25 or 50 data, and you divide them up into 5 classes, and 3 of the 5 classes are empty, it's just, okay, well, that's the data you've got to work with. Now, if you've got 100 data, and you divide it up into 25 classes with a class width of 4 each, and you find that, okay, I've got data in all my classes. Let's see, if I go to 30, will I get better resolution? You divide it up into 30 classes, and now you see, oh wait, I'm starting to see zeros pop up here. Now that tells you you've gone too far. But if you're only working with very small data groups, with small samples, you may not have any choice but to have some zeros. What happens if you leave out those classes? When you start plotting your graph, it's not going to be an accurate representation of the data. So you always have to have the classes must be continuous, even if your data set is so small that leaves some empty classes in your distribution. The classes must be exhaustive. That means you want to make sure that all of the data in your sample will fall somewhere in your frequency distribution. So it's every data value you get is going to be somewhere in one of those classes. It can't be in any of the other. It can't be in more than one, but every data has to be in one of the classes. This is saying we did about this is why we make sure that the boundaries match up. When you set up the classes, there will be gaps in the class limits, but not in the boundary limits. Number 6, the classes must be equal in width. Why? Why would you think that's the case? What if we made this one worked out? How did this one work out? Yeah, 54 to 62 was 15. 45 to 53 was 9. 63 to 71 was 10. What if we made the first one 27 to 44? Then, instead of getting a graph, that looks like this, we would get a graph that looks like this. And it would distort that portion of the graph. It would make it look, it might not change the arithmetic, but it would change the appearance of the graph. And the whole point of the graph is to make a visually accurate representation of the data. So, you always need, the classes must always be equal width. I don't know. Oh, they've got what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 5. They got 50 temperatures. Yeah. Ah. There is an exception to the always needing equal width. Who can tell me what the exception to that rule is? The hard and fast, absolute, always, every time rule is that the classes must be equal width. Now I'm telling you there's an exception. When would that exception be? No. No, but you have open-ended graphs. When you have open-ended data, when that first class doesn't end at 58, if it goes all the way to minus infinity, or the other side goes all the way to plus infinity, well, then your end classes, the two end classes, can be, one or both of them can be asymmetrical, can be unequal, can be a catch-all. But you will see as we go through the course of the semester that you'll be able to tell when that becomes when it becomes problematic and you need to readdress. You would have to reanalyze your classes. In the case of the example that we've been working here, they say the last class, instead of being 50, what was it, 54? That's a different class. Instead of saying the last class was 54 to 68, it was 50. It was what if the last class was 54 and over? Okay. Well, obviously there's not going to be an infinite number of. No one's going to be infinite old, but there's going to be. You might have a handful of people that are more than 54 years old. If you're talking about, I don't know, high school seniors. Probably not going to have a lot of more than 54 or older, but there might be one or two. There's always that 60 minutes special interest story about the 108-year-old grandfather who just finally graduated high school. Okay, so that's when you might have to make an exception to the equal class width. They work through a couple of examples here. I would really like to work through one of them, but we don't have time. So, just go through the rules, through the steps of how to work through these examples. First, determine the classes. Find the highest and lowest value in your data set. That is your total range. Decide how many classes you want to divide your data set into. Then divide the range by the number of classes. That will give you your class width. It may or may not be an integer number. They tell you here, round up to the nearest whole number if it's not. So in the case of this example, they say 34 divided by 7 is 4.9, and they're saying you would round it up to 5. We've already looked at how you divide up classes with fractional parts, decimal places, and then how you set about to establish the boundaries as opposed to the class limits. But The book may plan on introducing you to that more slowly. Once you have set up once you've decided, you've determined the range, you've established how many classes you're going to use, you've decided on a class width. In fact, if you try to make sure that your class width is an integer number, that may help you decide how many classes you want to do. If you can divide it evenly by a certain number of classes and get an integer value, great. Then, as we did in the example earlier, tally up your data. Once you've done the tally, sum up each tally into the frequency for that class. And that is your frequency distribution. Next time we will start talking about graphing those frequency distributions, the types of graphs that you can use to present them. At which point we will be looking at the one part that I didn't get to today, and that's the cumulative frequency distribution. Just basically, you start, if your frequency distribution is 1, 2, 5, 11, 13, 9, and 3, if that's your frequency distribution, then your cumulative distribution would be 1, 2 plus 1 is 3, 5 plus 3 is 8, 11 plus 8 is 19, 19 plus 13 is 32, 32 plus 9 is 41, and plus 3 would be 44, and that would be your cumulative distribution. That would be like saying, instead of saying 5 of the data were between 2.5 and 3.9, and you would be saying 8 of the data were less than 3.9. Or 19 of the data were less than 4.8. And they make a special kind of graph just for doing that kind of distribution. We'll talk about that on Wednesday. Any of you have any questions? Okay. Class dismissed.